Okay, so is it started? Yeah. Can you see it clearly? Okay. So just a quick reminder of what we had in the previous lecture. We talked about how fast is our modern computer is. Like this is supercomputer compared to all we had in the past. We talked about what the problems it could face, right?
Yes.
Because of the bad programming practices. And it can cause like the death of people if we don't program well, right? We talked about, do you remember the cycles of CPU? You haven't been.
I was not there.
Okay, so we have 4 cycles of CPU. First, what our central processor does, right?
Yes.
It fetches the instruction from the memory, from the RAM. Then it decodes it. Like instruction is a set of bits, so we need to extract the useful information from the instruction, right? From assembly language. Then it executes an instruction. For example, copy from register 1 to register 2.
Yes, and then give
right?
you the output. And then the output.
Right, and write back to some
Yes.
register. Yeah, so four stages. But our processor does this kind of parallel. So while one instruction is fetched, other is already decoded, other is executed. So it's kind of parallel pipeline. So I present to you, this would be my assistant. If you see this, then part of information from the slide would be an example. So you need to remember, like when you are preparing to the exam, you need to remember all the slides with this thing. Okay. We had overview. Okay, so briefly, we have different types of memory inside the computers. Do you know SSD, HDD?
It's the slowest one, I think, and
Right.
it's slower than main memory, and it has things that you need quickly.
Right. So main memory is RAM, right?
Yes.
Random access memory. It's kind of it's less in capacity, like 10 gigs compared
Yes,
to.
but it holds everything non-permanent. Yeah.
Great. And also it's faster,
Yes.
way more faster. And inside, this is peripherals, like it's outside of the processor.
CPU, yeah.
Yeah. And this is inside CPU. We have registers.
It's the fastest one.
Yeah. That's the memory which CPU directly operates with,
Yeah.
like combined to numbers and etc. Right? And do you know what is cache?
I'm kind of know. I didn't get the cache. They explained it to me, but I didn't get it.
Okay. So do you know we have arrays, right?
Yeah.
And because our memory is paginated, it's not, we cannot fetch one variable, okay, from the
Yeah.
memory. We fetch the entire page. And this page resides in L3 cache. The more local data from this page we access, for example, array, right? Array of
Yeah.
integers, like 1
That's
to
an
3.
L2, and then the specific one is an L1. Okay, got it.
L1 is also kind of for arrays, but it's just not to go back to main memory. It's
Okay.
cached here, some parts.
So it takes a part of the main memory and kind of separates it so register can then use it.
Right, correct.
Okay.
But for example, if you are randomly using array 1, array 2, array 3, right?
Mhm.
You switching between large pages of memory, that will lead to cache invalidation.
Okay.
So you don't have this information in cache. And processor will be, you can compare, like this one is 3-5 cycles and this is like 200.
So the
right?
higher we go, the less cycles you have, but more memory.
And less memory.
Less memory.
Yeah, great, thank you. So, the network model, do you know networking?
Yeah.
Okay, so you just need to know how, because we are learning the distributed system, you need to know how computers are connected together, right? So, can you point out, what is OCI model, OSI, do you know?
It's It's basically a layer of how the computer works. I don't know how to say it, like data link connects one node to another network. Yeah.
So we talked about this in the previous lesson. Why we have separate layers, for example?
They all have separate like tasks. They all have separate responsibilities. They also have separate responsibilities.
That's correct, but like the main reason why we need different possibilities, because we have different physical layers.
Yes.
Wires, fiber, like wireless, right? Technologies. And we have we need different protocols to operate here,
Yes.
and we need layers of abstraction. This layer doesn't know anything about how this is done. It only somehow uses an API, like interface provided. And this layer doesn't know about transport layer. It only uses like but always, you need to remember that OSI model is completely theoretical. It's not.
Yeah, it's not actual physical.
Physical is TCP/IP. We are using TCP/IP model, which is not good theoretically, but good practically, right? And protocols that we use. Most common on the application level.
HTTP, yes.
Yes. Great. Okay. Plan for this and next two lectures. We will talk about motivation to virtualize resources, how processing works, networking, containerization, and we will go to Kubernetes, I think. And as a practical work for the rest of your course, you will train to administrate and learn the insights of Kubernetes, because it's kind of a grid system.
Okay.
And even like CERN is migrating some of their resources to Kubernetes.
I have a question then.
Sure.
Should we bring our own computers?
For practical.
Yeah.
You can work here on those. You can bring your own. You can do it home. I will send the.
Okay, but do we need like a platform to write the code, like IntelliJ IDEA or something like that?
I will send all the instructions. It will be like from zero to hero. So, okay. Let's proceed. We are talking about grid, right? And we talked about the definition, right? It's not something. How to call this? There is no strict definition technically, right? OSI is a standard. It's described from like very thoroughly. Grid is not described. It's kind of a solution to some distributed problem of like connecting computational resources and dividing between different scientific organizations. And why grid? Do you know why grid?
White grid?
Grid. Why it's called grid?
Oh.
Right?
A wide array of computers connected to each other?
Right. I thought about the grid as a grid of lines, right?
Yeah.
But not exactly. It came from like power grid. Do you know power grid?
Power grid is for
Distributed electricity. Yeah. So it came from this term, like distributing the computing as electricity.
Okay.
Like you pay, you have resources, right? So. This won't be an example, the definition, because there is no clear definition. But the interesting point is non-trivial quality of service. We talked about this,
yes.
right? Okay. So, distributed systems, that's the best I have found, right? And why do you think we need different, like, you see the centralized, right? The users and the central server are interconnected like this. Decentralized and distributed. Why do you think we need different architectures of systems like
Well, because they act differently. In centralized, they're connected to the center, but not to each other. In decentralized, some sub-centers are connected to the center, but not each other. And distributed, everything is connected and has no center. So it's all different situational.
Correct, right? But why do we need this For what reason? Why we cannot do all the systems like this?
Because it's not practical. They're not connected to each other. Sometimes you need them to be connected to each other and not the center.
Kind of. If we will go back, there is a quality of service, right?
Yes.
At some point, you face the situation when this doesn't supply enough quality of service to the user.
Yeah.
So the users connected to a single server suffer from outages and like it cannot handle the
If
load.
it goes
right?
down, everything goes down.
We do, by the way, decentralized, availability, right? I don't like this word, but this is not highly available because if one node goes down,
Everything goes down.
yeah. And this one, do you know example of decentralized system?
Yes.
Most common. People are crazy about this.
Social media.
What?
Different social medias.
Kind of, but okay. I was talking about blockchain,
Oh.
but that's
No.
okay. Let's just go ahead, right? The quality of service. I will just repeat, right? The definition is strictly and formally defined. It means we have a formula for that, right? We measure, and the important thing is as experienced by users, right? So we measure something from the user. For example, I build the company and I want you as a user to have a best quality of service, right? As in a restaurant, right?
Yeah.
So let's go through this one. Centralized, single authoritative systems, right? What means authoritative? Means it controls everything.
All the other nodes.
Right. How? From the point of protocols or authorization, and it has, from my perspective, in the network, it has a single endpoint, single way. Okay? From the infra, atomic inseparable set of resources. If I drop one, everything
Yes.
is, yeah, right?
So it's not used, right? It's not good. It's not practical to use it then. If one drops, everything drops.
Kind of. We will talk about this. So that's interesting, right? It doesn't seem good, right?
No, it
Because
doesn't
of
seem good at all.
okay, but there's more about it. Decentralized, multiple entry points, no single authority, but authorities are still present, right? And we see it as a resource groups. What does it mean? If we take the subset, if there is one subset of our infrastructure, right? We have two computers, computer 1, computer 2, right? And they are working independently. So we can turn off one and the other will stay
Yes.
healthy, right? So that's decentralized. But actually, I want to show, like,
No use. That's why it's there.
okay, so okay, I will explain like this. So imagine if we have 3 nodes, right, and we need to get a consensus between them. We need 2 out of 3, right?
Yes.
So we cannot leave one node is unoperational. So because it. Okay, we will talk about this later. Okay, but just imagine that we lost the connection between one node and 2 other.
Okay.
This node doesn't know if those are still connected or not, so it cannot be eligible master. Only 2 nodes can form the cluster out of 3. That's a bit of probability theory, right?
Nothing though.
Okay. Okay, distributed. All the nodes work together as one logical system. It does mean that distributed also fails if we drop one node, because it's spread out on the service, not from perspective of it's not decentralized, right? functionality is
The
distributed.
whole thing is essential, basically.
Kind of. But what it means distributed, that any set of resources is working on a separate function, and they work all together. And if we drop one set, everything falls down because we dropped that function,
Yes.
right? So, but we can build both decentralized and distributed systems to have reliable and distributed computing. Okay. So just to compare, monolith is decentralized. What could we say? It's simple to test, deploy, develop because we develop one server, okay, with one piece of code. It's easy to observe, like take the logs and debug, but non-trivial to scale. You cannot scale it well, okay? For example, for geo-distributed, you still need to scale the database, for example, right? Because your clients are living in different locations. Distributed systems have this, like elasticity. We can add or remove nodes freely. Fault tolerance. If something fails, system stays operational. Robustness, throughput means the performance of the network. Geo-distributed, right? So we can distribute geographically, but it has high complexity. Okay, any questions so far?
No, I got it.
Okay, let's go ahead. All this thing is closely related to the big data. Do you know what is big data?
The ones on the servers. I kind of know, but I can't explain how I know. I don't
Okay,
know.
1 megabyte is a big data.
No,
100 megabytes?
I'm pretty sure no.
1 gigabyte? Okay, 1 terabyte.
1 terabyte is a big data.
Actually not.
No?
No? So the definition, it is done, this definition is given by a person who worked on Google on the, BigQuery, project.
Yeah.
Yes. Great, you have fundamental knowledge. So that's top number one from algorithm, sorry.
You
From-
can speak it Russian, I understand.
No, others won't.
Okay.
So, from the point of algorithm, it's most advanced. It's like super cool.
Yeah.
And he formed two definitions of big data. One, if the data exceeds the capacity of the single machine.
Okay.
So we have the terabyte storage, right? So we can put the terabyte on single machine and process it here. So that is not a big data. And the data that is cheaper to store than to analyze. So we have constant flow of the data, for example, likes by user, right?
Yeah.
And we cannot analyze them right now because we don't have such human capacity. We just store them on the disk. Okay, so that's it. The difference between cluster, grid, and cloud. Cluster is a set of homogeneous resources. So in the cluster, when we mean cluster, we mean that all resources are the same.
Like a bunch of servers in a room.
Right.
Okay.
But we are like, we mean that they are almost uniform, like almost the same. The grid is highly heterogeneous, like it can have GPUs and a lot of resources.
Multiple different things connected to each other.
Right.
Okay. And cloud is all software and non-physical.
Right. Cloud is kind of thing that pretends to be a grid and pretends to be a cluster for your money. So you pay money, you get grid, or you pay money, you have a cluster of machines. Because you can, in the cloud, for example, in AWS, right? You can build like the cluster, and on top of that you can connect VMs, you can connect firewalls, like
But if you don't
different
pay
types
after
of the
that-
system.
But if you don't pay after that, it's not yours anymore.
Yeah, of course. So, but also cloud is virtualized. So you don't, if you even get the, for example, they give you a server. You never know it's a physical server or not. Because it can be like, I don't know, Raspberry Pi running some emulation of iron or something, I don't know even. Okay, so that's the definition. Oh, I forgot, this would be on exam for sure. That's the main difference. Cluster homogeneous, read heterogeneous, and cloud is a very virtualized, so we don't know. Okay. Okay, how many time do you have?
I have time for the full lesson.
Okay, so 2 hours
Yeah,
is okay?
Yeah.
Thank you. You abandoned ethics?
Yes.
That's
Literally, I
that's very
did.
important for computer science.
I like money, so you know.
Thanks, okay. Because I need someone to talk to. Okay, so before we jump into the distributed systems,
Yes.
let's see how like general computers handle multiple processes. Do you know?
I'm pretty sure they do it like kind of simultaneously, but the first one takes the precedence over the one that was later ordered.
Right. So that's for single core, right?
Yeah.
For single, if we have only one CPU, right?
Yes.
Core, it kind of, we see like we can still run multiple programs, right?
Yes, but it has a queue.
Right, exactly, as you said. So exactly what you said is the concurrent execution. This is called concurrency. For example, we have a one function, right, set up, and we have 3 tasks with infinite loop, like they are spinning up infinitely.
Yeah.
Okay. How one CPU can run this simultaneously? Because we have, for example, let's pretend this computer has one CPU. It still can play sound. It just switches between the tasks very quickly,
And
right?
you don't notice.
Yeah. Human eye won't notice that it's switching between those 3 tasks, like very quickly. Let's see the diagram. So, but do you know how it switches exactly?
Like it has a very small waiting period between the tasks. You don't notice it, but it's like there. So in that waiting period, it switches.
Okay. Yes. But also on each tick of the, because it can even switch in the middle of instruction, some processors.
It can.
Why? Because it has a tick timer.
Oh.
Every from the point of hardware we have a timer running, and every time it ticks, it runs the so-called ISR or IRQ. That's the interrupt routine. What it means? It interrupt
Interrupt the task.
yeah. Basically, it changes the current program pointer, like the number of instruction on the CPU. It changes it to different one. For example, you see, there was an interrupt, then task A interrupt. We still proceed with the task A. Then task A finished. We still idle. So we can switch tasks only by these interrupts. Yes. When the interrupt is called, it's called preemption. So when one task switches to another, it's called preemption. Okay. So let's leave it to the second lesson, like the next lecture, because the difference between the okay, let's just leave it for now. Okay, because that's not fair, because we have multiprocessing, right? That's you see, it's kind of like a snake, right? So we can have multiple like processes running in parallel, but not more than we have a CPU's count. For example, we have 8 CPUs, we can have 8 threads running, but
no more than that.
yeah, simultaneously. But it could be like modern computers can run 10,000s of threads due to switching, right? They switch. but simultaneously only how many cores we have. Okay, and that's the definition of task. Discrete unit of work, right? Submitted to the system, and we will work. Exact definition will be in distributed systems, right?
Yeah.
Discrete unit of work submitted. Interrupts signals that temporarily hold the CPU and switches the task. Preemption, forcibly interrupting the running task by operation system, right?
Yes.
Or switching to another task. Okay, so you already know who does the switching, right?
The CPU.
Not exactly. CPU does the interrupts,
Okay.
but the switching does the operation system.
Oh, okay.
Operating system manages it's like the policeman.
Yeah.
Okay.
I forgot about
No, that's great. The answers are perfect. Like, trust me, I have different groups. They don't know like zero, absolutely. So, operating system is, we run this on top of the hardware, right? We have the microchips, right? And then microarchitecture is the set of instructions this thing can,
work on.
yeah, ESA, instruction set. So like, I don't know, call people register,
so like
jump.
the tiny things on the motherboard, the tiny engravings on the motherboard, is that microarchitecture?
No. Microarchitecture, for example, it could be ARM or x86.
Oh.
It's like assembly language that CPU understands.
Okay.
The binary code CPU understands.
Okay.
Because, for example, if you take the program from Intel Mac, do you have MacBook? If you have Intel MacBook, if you take the program, same, right? And move to M1 MacBook, it won't work, right? Because it has different microarchitecture. It has different, we will talk about this also. Operating system is running on top of that and supplies all the programs running and supplies the resources. Let's take a look. The simplest one, operating system, ever known, FreeRTOS, free real-time operating system. Hardware layer, like drivers, right? How we handle the interrupts, file system, drivers, networking, timers. That's just you understand, right?
Yeah.
Okay, so drivers is just code to use the hardware, right? The scheduler manages.
When the tasks are executed.
Right. So it decides the order of execution. It could be round robin, like by turn, right? It could be how's it called? Priority queue,
Yeah.
right? As you said, it's a queue. Exactly. It could be priority queue. So task 1 could have higher priority, so it will preempt task 2 from running. IPC, do you know how it's?
No.
Inter-process communication. So tasks could communicate between them.
Yeah.
But because it can switch in the middle of instruction, we need a special mechanism called the logs. Like all of this in this small module IPC, because we need to, like, if some resources are acquired, right? If I'm using, for example, I don't know, if I'm using this computer, you cannot just go interrupt me and use it. It's the same because I locked it. Okay, so that's analogy. And security module is for fast computing of, for example, the checksums in network protocols. Okay, so that's the simplest system. But on this OS, we can build this. So this is totally on FreeRTOS, DJI drones. I just encourage you to see how simple it is and how good is the result, okay? And we have a Linux.
It's a jump.
Yeah, not really, but it just way more harder to understand because it's so complex. And
But
you
that's
see,
also because it's open source, right? Everyone can add something to it.
unfortunately, everyone can add
That's a
something.
good part about it.
Not really. The Chinese hackers are very happy because they can add their code, and nobody have noticed yet. Like recently, was one bug, for example. They introduced a small change in the archiving algorithm, and with that they like intruded into the data centers and mined Bitcoin. So Chinese hackers happy about the complexity of the stuff because trust me, it's now okay. Linux grow 10 years ago it was like 15 million lines of code. Now it's like maybe 40 million because everybody adds and adds here. So the kernel is now huge because of the drivers maybe, but we see all the same, right? We have tasks, we have virtual memory. It's used for when you don't have enough memory.
Yeah, and you use that. It's like a heap memory, right?
No. If you don't have enough RAM, okay?
Yeah, you use virtual memory for that.
Right. There is a small section on your computer called, on the hard drive, called the swap. And swap means exchange, right? So if you don't have enough memory, put something on the swap, something unused. And when you need this to run the task, it just changes the content between, like it uploads something to the swap and takes back some useful into the RAM. So, but you can imagine how slow it is. Okay? So we have networking. So pretty much everything programs use, right? They use through the operation system. We don't write in the programs. We don't write own networking stack. Okay, we use TCP UDP from the system, and that's very important. So we heavily rely on operating system, heavily, like for many things, and multiprocessing is a and where was the scheduler? Okay, here's the schedule, right?
Yeah.
So it's kind of similar, but if you understand this, so you might also understand this. But the good thing I just wanted to show, we can profile this. We can measure how good we are working on every level of that previous level. Those are all programs for measuring the stuff. That's about quality of service, okay? Okay, sorry. So now, how do we run our programs? How do we write programs?
Well, I input the program from the human side, then to roughly say it gets translated to the low-level binary, and then the processor analyzes it and then gives you the high-level human understandable code or output.
Great. So we have human readable code, for example, in C on any programming language, and we have a program called compiler, but that is compilation is slow, and it just translates our code into binary code that CPU can understand.
Yes.
Do you see any problem with that?
Slow and
It's slow.
tedious and not really, like, if it's a big source file, then it will take a lot of time.
No, it really don't take a lot of time to translate. It takes a lot of time to
Retranslate?
link between the libraries.
Oh.
For all of this, we have separate libraries. And to link every function in our code, the linker takes a lot of time. Like modern compilers are very fast, except for linkage. Like they just transpile very fast.
But it's still fast then, yes? If except for the linking part, it's
Linking
fast.
is very slow.
But then, I guess for humans it's so fast then, because no one complains about it.
about compilation.
Well, I'm talking from the user side. No one really complains about it. If it's-
Because you're running on your computer, you're already running the binary code only that CPU can understand. Like those are instruction set. Okay?
Yes.
And you're running only this. You don't see how compiler works.
Okay.
And why it is so slow and why? Okay, so for example, I have a really big project on C
Yes.
related to security, and it compiles 2 hours. Maybe translation takes 5 minutes, but the whole compilation takes, on C++ actually, takes like hours, okay? But you only run binary code. Important thing is binary code is interpreted by processor.
Yes.
Okay, so it takes one instruction, executes, goes to the next instruction.
Okay.
Okay, just for the sake of
I think I'm understanding. So you're saying the users get the pre-translated, already compiled binary,
right,
but actual compiling during development takes a lot of time.
right,
Okay.
right. For C and C++, for Go language it's fast because it doesn't do linking in the same way.
So the lower the language, the faster the compiling. By
no.
low, I mean the understandable to the computer.
Sorry, say again?
By low, I mean the ones that's the closest to the binary.
Okay, not really. Just the Go was developed to be fast. Okay, so they had this purpose. C was developed to run everywhere. That's why it's slow. I cannot quite explain, but only Go language is fast compiling. Like it's rare. Like what they did, they really did very complex algorithms which speed up the compilation. But it's still, and it links everything statically. So we will talk about this later. But the problem with this, you see, the user only runs what you get exe file, right, or something that's already a binary.
Yes.
So we don't compile code ourselves, but it is written on instruction set, which it was compiled to. Okay. So the problem is, if we need to compile, okay, and from the operating system perspective, it's not enough to have the instructions transpiled. You need to have some headers in special format to run your executable. For example, exe file, right, in Windows. You need to fill a lot of fields for that, like to just run your program, okay? And on macOS, it's kind of simple. On Linux, it's like dummy simple. So the problem with that, executables are operating system dependent. Because of libraries, because we use the facilities of operating system, and because of this one, because we need to have different executable formats. Also, it's different for Android and iOS, like
Yeah, they need their own languages.
like APK and like. So the problem with compilation, we have different architectures, like set of like language that computer understands,
Yes.
right? Binary language, ARM x84, 86, right? RISC-V, that's an open architecture. Like we have all the different, and we have 5 programs, okay? For example, we have 5 programs, 5 architectures.
Okay.
How many times we need to compile?
5 times. 5 programs, 5 architectures, program 5 times.
For each program. Like we have 5 programs.
Yes.
Okay, 6. Here's 6, right? And 5 architectures, different. We want
30 times, you have
every
to compile 30 times.
yes. So it like multiplies. We need to do a lot of compilation, right? There are languages like Java and Python, which are interpreted. What that means? From
Well,
the
they run on Java Virtual Machine. Virtual Machine interprets them specifically for every single OS. I know that because I studied Java. Yeah.
You had good course of Java? No.
No. Mostly I study by myself, so I don't know. I do not attend.
Oh, okay. So you haven't attended, right, Java?
No, I did by myself.
Okay. Because I'm conducting Java for different group, and I need something to compare with, like how it's done here in the university, because they know zero. No, someone learned by themselves, but that's bad. Trust me. So you're absolutely right. We need like tiny kind of interpreter, right? Like translator,
Yeah, that's Java virtual machine.
right? Java virtual machine on every platform, and we still compile our code, but to bytecode. It's like intermediate. We have these architectures, right? But we can develop our own set of instructions, right? That we know. That's the bytecode, and then we on each like those are separate computers, right?
Yes.
On each of that, we just interpret the code, especially for that platform. So we need now how many compilations?
Only three? Well, because I write the code, it compiles into bytecode, and then it goes to these three machines. So we only need three.
No.
No?
If you compile one program, you need to compile one time.
Yes.
Okay? And you have bytecode
Oh, I
which
have to
can be
compile
run.
one time for all the.
Yeah.
Oh.
Because this virtual machine, virtual
Yeah.
machine means like virtual CPU. It already understands. That's like people talking in different language, right? I can already understand your language and translate to Windows language, okay? Or like any platform. So, but we also need to have this compiled for this compiled for this, like JVM compiled.
Okay.
Okay, so, but if we already have them, we compile once, run everywhere, right? Just source code, we understand, right?
Yes.
Bytecode, which is kinda our tricky language, right? And this is, during the interpretation, we translate it to different assembly languages.
This is code 64, right?
Where?
This is code 64, the last one.
Yeah, x86. The one you have AMD64 architecture, like instruction set. That's like Intel AMD processors are running this one. So we just need to compile once, and this one, like interpretation, will be done by Java virtual machine. Okay? Python works the same way, but it has the compiler in the interpreter, so we cannot really compile, like do bytecode. We just input the source file, and the interpreter like runs all of
But
it.
isn't Python built on Java machine? It uses Java machine, right? Or am I wrong?
No.
It's not-
Python is written on C.
Oh,
It has its own bytecode
yeah.
language, and like actually it's a bad language, Python. I'm senior Python developer.
I am studying it now. It looks simple. It's not. Should I get ready?
That's very bad. From the perspective, you cannot write the reliable software on it,
Oh, why?
which will run because God made Python bad. I don't know why. It is very slow, inefficient, and it has so many different aspects. You might know how it works, okay? Like the global interpreter lock and all that stuff. And you can spend the whole life studying how Python interpreter works, but it's still, actually, it's easy to just compile the program.
Just write the source code and let everything else work, right?
The compilation is the easiest one because this is very slow. We talked that this can be slow, right? But this is also like interpretation of the code, like translation,
Yes.
could be also very slow. Okay, and for example, Java is also very slow because of that on the start. then it uses internal caches and it heats up, and actually it's fast in the end, but still Java is slow. Python is always slow. Like do you know there are many interpreters for Python? One is CPython, you might use, the most common.
Yes.
And there is PyPy, which does JIT compilation just in time, so it's compiled to Python. It's actually fast, so compared to this one. So,
Is that Python not used as much, or is it used more than CPython?
sorry, say again.
Is the one that's the faster, is it not used as much
No.
as CPython?
No.
No?
Because CPython, everything was developed for CPython.
Oh.
It has some differences.
Okay.
Because it's like implementation of in the interpreter is running on the your computer, the user computer,
Yes.
right? Not the developer. The developer provides only the source file in this case, because compiler is already been dedicated. But it's like implementing the interpreter from zero. Like
So there are fast compiler languages, but everything is made around slow compiler languages.
Right. And okay, so we have option 2 is
Yeah.
to interpret our programs, right? So from what we have studied, binary formats are different because of the operating systems and assembly languages, right? And because of that, compilation time is slow because we should go through a lot of code, OS dependent, etc., and link between them. The problem with interpretation is the version. For example, for Python, you can have a version of libraries and version of interpreter. For example, Python 3.12, and the old code might not run on you, and new code won't run on old interpreter. So this one is also inefficient, right? Interpretation is kind of slow. So that's the problem number one with operating systems running binaries. What is linking? Okay, so when you run a process, right, any of them, all the instructions are loaded into memory. Like all the binary you have are loaded into the RAM.
Yes.
Okay? And also the libraries should reside here because CPU only can execute from RAM. It cannot execute from this. We talked about virtual memory, but it slows. Only RAM is the place CPU can run programs from. So there's two types of linking, okay? For example, if we have some library, right? For example, for making HTTP requests, we can compile it with the program inside, okay? But if we have like hundreds of programs with the different libraries linked statically, we need a lot of RAM.
Yes.
Because each of them are loaded into RAM, okay? But mostly programs use same libraries. So we can,
So it's going to use dynamic link.
right? We kind of can hope that, like we can say, okay, we hope that you have this library already in memory,
Yeah.
okay? And all the programs will use it by using the addresses, in-memory addresses of the functions. Because addresses from perspective of processor, address of instruction here is the same for all the programs, okay? So dynamic linking is like we only run the programs above the shared libraries, okay? But the problem that you have seen this, right? The library was not found, reinstalling the program may fix. Okay, so that's bad, right? Libraries can occupy too much RAM if linked statically, if not, if we link that dynamically. Also,
Could be
libraries could be different version. and they could be missing on operating system. Okay. So any questions? I will take some water. By the way, wait.
But I had this problem when I was little, and I still can't really figure it out. If my library, I have the library on my system, but it has the wrong version, how do I update it?
Download new one and put in the.
See, I was trying that. I was trying to do that. Maybe it's because I was little and didn't understand. But it wasn't downloading. It said I didn't have enough memory. Then I deleted everything, but I still did not have enough memory.
It doesn't. Okay.
I downloaded it.
Okay.
I tried to download it. It said I don't have enough memory. I was like, okay, I'm gonna delete everything to free the memory up. I still did not have enough memory.
Okay. That's kind of interesting. Maybe you caught a virus or something.
Maybe.
No. So on the Windows, on the Mac, it's kind of impossible to go to. Like the viruses on the Linux and Mac, it's not really a problem because they built good for security. In Windows, you need antivirus, so your PC will die. Okay. So we had this problem, right? And this with the operating system. This is mostly the problem with the environment we are running programs on. So people thought, okay, we cannot compile statically, we cannot do this and that. How do we get the isolated, secure, reproducible environment? Do you know how they managed to do that?
How did that finish?
Okay, so what means reproducible?
You can recreate it multiple times.
Correct. So do you know any way to do this? Have separate, same environment each time?
Get the CPU and transfer it to that. I don't know. I don't know.
Then virtual machines.
Oh my god.
Virtualization. So we can separate on the hardware level. We can separate your computer in that way that it will simultaneously, like in the same time, run two operating systems, just switching between them. So for example, two cores will run Linux and two cores run Windows, okay? So that's virtualization. Like that was first idea, let's run the whole operating system, okay? With the needed libraries and all the stuff, like
all the
isolate.
software for different OS, right?
Right. Because we need different OSs, right? And
they have different structures.
That was the first thought. We have type 1, type 2 hypervisors, but it won't be on exam, just for your like general information. Type 1 runs pure on hardware and like separates the resources of hardware like evenly, okay? The type 2 runs on the host operating system. Have you had like VirtualBox?
I had BlueStacks, which is basically I'm running mobile OS on my computer while also running my computer.
Nice. Like yeah, so you have host OS and you have hypervisor, but actually mobile OS it's rather emulating, not virtualization.
Oh.
It's like transpiling the. We have different instruction set, and we can translate from one to another.
Okay.
For example, from mobile instruction set, I run to your computer. But anyway, we will use this one in our practical work. And do you know what is virtual machine image?
I will read it and I will tell you.
Okay, so that's just a file that contains all the needed files for like the zip archive, right?
Yeah.
Which contains all the files that operating system needs to run.
So it's a library of an operating system, basically one big library.
Not really, but rather like
It's
the
not-
snapshot of
Yeah.
the snapshot of hard drive.
Yes.
Okay? Like if we will take everything you have on the hard drive and we'll make a compressed like archive out of this. So it contains like base system files, libraries, programs, maybe some programs to connect to like the host OS. Okay? Oh, so you have written like if we are running this, we have guest OS, which we have like virtual machines, and this is physical. It's not virtual. It's like host operating system. So host and guest, just to remember. Okay. So this is like virtual machine image is just like the state of file system of this guest OS. So if you change something here in VM image, it would change. But you can create a snapshot in certain period of time. For example, before you have started lab,
Yeah.
and if you have like destroyed your OS, like the deleted base system, you can flash back and recover from base image you had
So a
previously.
saving system. You save, like in games, you have a saving system.
Yes, like it's a save of our operating system. Okay. Okay, so I think that's it, right? Any questions?
No, it was pretty clear.
Okay, I hope. Thank you for your attendance. Let me disable this one. I hate my voice, so. Okay. Would you mind